morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about impedance matching of a transmission lines as one of the topic in electromagnetic waves and transmission lines. So, in the previous lectures, already we have discussed the electromagnetic waves concepts and the propagation of different types of medium. Then, now in the early lectures, we have been discussing about the topics which are available in transmission lines. Now, one of the topic in transmission lines is impedance matching of transmission lines. So, what is the need for impedance matching? To get maximum power transfer, there is a need for impedance matching. Means the source impedance which is connected at the input side must be equal to this load impedance which is connected at the output side. This is the case, we can transfer maximum amount of energy or power from one point to the another point or one place to the another point. So now impedance matching. So what is the need for impedance matching? What do you mean by impedance matching? What are the different parameters affected based upon this impedance matching? After that, we are going to analyze different types of impedances cases. Then in that, different types of wavelengths lines. Based upon that, the relation must be established as the input impedances with the load impedances along with the characteristic impedances. Now first, impedance matching. So impedance matching is required. What is the need for impedance matching? Means impedance matching is required to minimize reflections. Means whatever the signal which is sending or whatever the energy or whatever the power or the signal which is transferring between two media, means there is no reflections or occur in the medium 1 case. Here impedance matching is required. Means impedance matching is required to minimize reflections and by making the load impedance is equal to the source impedance, where source impedance is denoted with ZS and load impedance is denoted with ZL. Right? So here load impedance must be connected at the output side and the source impedance must be connected at the input side. Right? So to minimize the reflections and in order to equate load impedance with the source impedance, then we require impedance matching. Right? So if the source impedance that is denoted with ZS and the load impedance is denoted with ZL and the transmission line characteristic impedance is denoted with Z0 or purely resistive, means ZS, Z0 and ZL are purely resistive type. Right? Then reflectionless matching is occur, then that is the case maximum amount of power need to be transferred. Hence the name is given as impedance matching. Right? So in order to minimize or in order to reduce the reflections of the waves and in order to equate load impedance with the characteristic impedance, then we require impedance matching. Then when the impedance matching is to be done, means the source impedance ZS and the load impedance ZL and the characteristic impedance of the transmission line are purely resistive type. Then the reflectionless matching is occur. That is the case maximum amount of power is to be transferred from transmitter to the receiver or source sender to the destination end. Then impedance matching of RF transmission lines. So affected parameters based upon this impedance matching are given by here is basic requirements needed for a better transmission line. Is the first one is high transmission efficiency. Generally it is denoted with eta, means efficiency is denoted with eta, and in order to get high transmission efficiency, then in order to get very small VSWR, means voltage standing wave ratio, then it is denoted with S, which is equal to 1 plus gamma by 1 minus gamma. Means in order to reduce the reflections, then here very small VSWR is to be available and can be able to operate over a range of frequencies at high frequencies range, and all the above will be affected due to mismatching of impedance, right? So these are all the problems, means based upon this impedance matching of a RF transmission lines, radio frequency lines or UHF lines, then these are the parameters or basic requirements needed for the better transmission. The first one is high transmission efficiency and low VSWR, nothing but voltage standing wave ratio, and can be operated at all the frequencies like high frequencies, and all above parameters are affected due to the mismatching in the impedances. Okay, this is about impedance matching. Means why we need impedance matching, means to get or to reduce the reflections, and in order to equate load impedance with the characteristic impedance, based upon that to transfer maximum amount of power from one point to the another point, we require impedance matching. Okay, now different cases of impedance matching, means here impedance matching is occur in two different cases. One is related to the depending upon the wavelength lines, and depending upon the stub matching. Basically, there are two types of impedance matching cases occur. One is depending upon the wavelength of the transmission lines, and one more is depending upon the stub we are adding to that transmission line is gives us here stub matching. So depending upon this wavelengths, here three cases are occur. One is depending upon that, means lambda by 2, lambda by 4 and lambda by 8. And here there are two different cases are available in this stub matching case. One is single stub matching, and second case is double stub matching. Single stub matching and double stub matching, right? So basically the classification related to impedance matching means depending upon the wavelength of the transmission lines and depending upon the stub we are adding to that transmission lines, there are two cases are there, wavelength lines and stub matching. Under this wavelength lines, depending upon that wavelength, will have different types of lines called lambda by 2 wavelength line, means half wavelength lines, and a quarter wave lambda by 4 is said to be quarter wavelength lines, and lambda by 8 is said to be eighth wavelength lines. Then depending upon this stub matching, we are adding, if we are going to add single one, then it is said to be single stub matching. And if we are going to add the second, means two types of stubs to the transmission lines, then those two are said to be double stub matchings, right? So first we are going to discuss about, in this lecture, we will concentrate on this wavelength lines, or depending upon the wavelength of the transmission lines, three classifications now we are going to learn in this particular lecture. Now after that, we'll continue with the single stub matching and double stub matching. Is there any drawbacks which are exist in the single stub? In order to eliminate all such drawbacks, we are going for next one is called double stub matching, right? So this concepts and all we are going to continue in the next lectures. Now in this particular, we will be concentrating on wavelength of lines, transmission lines. So here the classifications are depending upon the wavelength lines. Half wavelength lines are also called as lambda by 2, and the quarter wavelength lines also called as lambda by 4, and eighth wavelengths are called as lambda by 8. So out of all these three, important one is impedance matching device, or it acts like inverter, means quarter wavelength lines. How the input in all the three cases, how the input impedance is related to the characteristic impedance along with the load impedance, we are going to learn in this particular lecture. Now after that, the second case of impedance matching is depending upon the stub we are going to add for that respective transmission lines as a single stub matching and double stub matching, right? So this is the classification related to the impedance matching. Now we will see in detail about half wavelength lines, quarter wavelength lines, and eighth wavelength lines. Depending upon the wavelength, half wavelength line. Generally, that wavelength is denoted with lambda. If it is denoted representing with half, then it is 1 by 2 into lambda gives us lambda by 2. Hence, the name has given half wavelength line. If the lambda value is to be subtracted, means divided with 4, means that type of wavelength lines are said to be quarter wavelength lines. If it is for eighth, then eighth wavelength lines. Now we are discussing here related to half wavelength lines. So what do you mean by half wavelength transmission line? Now, how the input impedance and the characteristic impedance are to be related is given by here first. It is a lossless uniform line of length lambda by 2. So, lossless, as the name itself resembles us, there is no loss in the signal. So, in order to consider the input impedance relations for lossless uniform line, which is having the length of lambda by 2, then how its input impedance is equal to the characteristic impedance or load impedance. Now, depending upon that, we are going to derive the relations, right? So, it's in this case, half wavelength lines case, its input impedance means Z in. We are representing the input impedance with Z in is equal to the terminating impedance or nothing but ZL or Z naught. Okay, so depending upon this, its input impedance of a half wavelength lines is equal to the terminating impedance. This is the relation we are going to derive now. Now, in order to derive that, firstly, we will let me introduce first what actually input impedance relation of a transmission line. First, we will consider lossy transmission line. Then, based upon that, if you are going to substitute for lossless line, then in that we will assume all the assumptions related to this wavelength along with the phase constants. Okay. Now, first, in the previous lectures, we have derived that input impedance of a lossy transmission line as Zin is equal to Z0 into ZL plus Z0 tan H gamma L by Z0 plus ZL tan H gamma L. Okay. So here H resembles hyperbolic functions and gamma is for the propagation constant and L be the length of the transmission line. So here if gamma is exist means gamma is nothing but propagation constant and it constitute the two relations as given by gamma equal to alpha plus j beta, right? So where alpha is exist means if gamma exists means alpha is also exist. If also alpha is exist means alpha is nothing but attenuation constant. Attenuation means there is a loss in the signal. Reduction of the amplitude is said to be attenuation. Then there must be, if alpha is exist in the signal, then there must be some loss in the signal. Hence, if gamma equal to gamma is exist means this is the equation which is called as input impedance of lossy transmission line equation. Okay, so in order to evaluate means half wavelength lines are analyzing for the lossless uniform line. So for that lossless means we are going to assume gamma equal to alpha plus j beta equal to. As we know that gamma can be expressed in terms of all the primary constants of a transmission line, that is gamma equal to root over r plus j omega L into t plus j omega C. Along with the all primary constants, then operating frequency, then propagation constant gamma can be given by here. And for a lossless means in order to get lossless one, we must assume R is equal to G equal to 0 in that particular. See, if we substitute R and G by zeros, then J omega L into J omega C is left over, which is equal to J omega root over LC. But gamma can be given by here alpha plus j beta, which is equal to j omega root over LC, right? So, if you observe in both sides, if you compare both sides, real and imaginary terms, if a real term is considered to be as alpha, that is alpha equal to 0 and beta equal to omega root over LC, right? So if we substitute here gamma by alpha by 0, then gamma becomes j omega root over LC. Nothing but if you substitute here alpha by 0, then gamma is given by j beta only. Right? So in order to simplify this one, we will consider one of the assumption as tan H gamma L is to be written as tan H j beta L. So from this, tan H j beta L is given by j tan beta L. According to the mathematics, the formula for the hyperbolic functions, tan H j beta L is equal to j tan beta L. Right? So in place of this tan H gamma L by tan H j beta L, and that is given by j tan beta L, then this becomes given by here Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Okay. Now in order to simplify or in order to get the relation between input impedance of the characteristic impedance Z0 or load impedance ZL, we must assume means for a half wavelength line, we are assuming initially L value is equal to lambda by 2. Right? So there is no alpha which is present in the input equation. Hence, this is the equation called input impedance for the lossless transmission line. Okay, that's why we are supposed to consider lossless line input impedance of a lossless transmission line, that is given by Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Now, in that, we just consider beta by, according to the phase constant beta, the formula is given by 2 pi by lambda. Or in general, this lambda can be given by lambda equal to 2 pi by beta. Means, the wavelength is going to change after every 2 pi radians. Hence, the wavelength can be given by here lambda is equal to 2 pi by beta. Now, from this, beta equal to 2 pi by lambda. Right? So L is equal to lambda by 2 and beta equal to 2 pi by lambda. Now substitute in place of beta by 2 pi by lambda and this L by lambda by 2 in this particular equation, then Zn is equal to Z0 into ZL plus JZ0 to tan beta is nothing but 2 pi by lambda and L is nothing but lambda by 2. By in the denominator also Z0 plus JZL tan 2 pi by lambda into lambda by 2. Right? So here if we simplify these two means 2 pi by lambda into lambda by 2. So this two gets cancelled. Lambda gets cancelled. What is the equation term which is left out? Pi only. Right? So now from that if we get cancelled lambda and lambda 2 and 2. Here also 2 and 2 lambda and lambda gets cancelled. Then Zn is equal to Z0 into ZL plus JZ0 tan pi by Z0 plus JZL tan pi. Okay. So here, see. In this case, the similar way, the lambda 2 2 and here also 2 2 lambda gets cancelled, which is equal to Z0 into ZL plus JZ0 tan pi by Z0 plus JZL tan pi. Right? So as we know that that's tan pi value which is equal to tan 180 is sin pi by cos pi. So sin pi means its value is 0 by cos pi value is -1, then it becomes 0 only. Right? If you substitute here tan pi by 0, then it becomes Zn is equal to Z0 into ZL plus JZ0 into 0 by Z0 plus JZL into 0. Okay. Then Z0 into here, this total term is 0 and this total term is also 0. Then ZL by Z0 is left out. So here Z0 and Z0 gets cancelled. Zn is equal to ZL, where input impedance of a lossless transmission line of half wavelength line is given by Zn is equal to ZL and that is nothing but Zs also. Right? Input impedance of a lossless transmission line is equal to the load impedance of a lossless one, nothing but source impedance of a lossless half wavelength transmission line. Okay, so according to the previous definition here, it is a lossless uniform line of length lambda by 2, and its input impedance is equal to the terminating impedance. Means input impedance is given by Zin and terminating impedance is connected at the load, hence it is equal to ZL. Right? So where terminating impedance is also called as load impedance, which is to be observed at the output side. Okay, so this is about half wavelength line of a lossless transmission line. Okay, next, if you're increasing the lambda value by, means next type of wavelength line is said to be quarter wavelength line, means its length is given by lambda by 4. So it is a lossless uniform line of length is nothing but lambda by 4, and for a lossy transmission line we know that input impedance is given by Z0 into ZL plus JZ0. There is no Z here. ZL plus tan H gamma L by Z0, ZL plus Z0, Z0 plus ZL tan H gamma L. Okay, here also gamma is exist, means attenuation constant alpha is also exist, hence this is the equation called lossy transmission line. But we are talking about lossless transmission line, means for alpha equal to 0, then gamma becomes J beta. Now in this case, tan H gamma L is equal to tan H J beta L equal to J tan beta L. Okay, then the relation is given by here. Input impedance of a lossless quarter wavelength line Zn is given by Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Right? So now consider this as the input impedance of a lossless uniform line, and where L is to be assumed as the lambda by 4 and beta can be given by 2 pi by lambda. As the definition which is given for the wavelength as lambda equal to 2 pi by beta, how the wavelength is to be defined? According to that lambda equal to 2 pi by beta means the phase changes are to be changing according to the, means after 2 pi radians. Hence, the wavelength lambda is given by 2 pi by beta. Now beta equal, then from this beta equal to 2 pi by lambda. Now beta equal to 2 pi by lambda and L is equal to lambda by 4. Now consider this is the equation for a lossless uniform line which is having the length of lambda by 4 of input impedance. Then Zn is equal to Z0 into ZL plus JZ0 tan beta L by ZL Z0 plus JZL tan beta L. Now in that, if you substitute beta by 2 pi by lambda and L by lambda by 4, then Zn is equal to Z0 into ZL plus JZ0 tan 2 pi by lambda into lambda by 4 by Z0 plus JZL tan 2 pi by lambda into lambda by 4. Means again, if you simplify that one, 2 pi by lambda into lambda by 4. Means this lambda and this lambda gets cancelled, 2 and 4 gets cancelled, which is left out here, pi by 2. As we know that tan pi by 2, its value is equal to infinite. Right? So in order to simplify this one, we just strike off here lambda, 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 2, 4 and 2, 4 gets cancelled. Now from this, we will be getting here. So Zn is equal to Z0 into ZL plus JZ0 and 2 pi by lambda by into lambda by 4 and 2 gets cancelled by denominator ZL plus JZ0 JZL tan 2 pi by lambda into lambda by 4. Here also this 2 gets cancelled, 2 and 4 gets cancelled, which is equal to here Zn equal to Z0 into ZL plus JZ0 tan pi by 2 by Z0 plus JZL tan pi by 2. Right? Now from this equation, Z0 into, if you take in the numerator from, if you take tan pi by 2 as common, then tan pi by 2 into means ZL by tan pi by 2 plus jz0 by. In the denominator also, if we take tan pi by 2 as common, then this becomes z0 by tan pi by 2 plus jzl is left out. Okay, so in the both the numerator and denominator, if we take tan pi by 2 as common, these two gets cancelled, then z0 into, see, zl by tan pi by 2. What actually this tan pi by 2 value? Tan 90 or tan pi by 2 is equal to infinity, right? So if you substitute in the denominator, means zl by infinite plus jz0 by z0 by infinite plus jzl. So something by infinity means this total term tends to 0, this also tends to 0. Hence z0 into jz0 by jzl. Okay, so this j gets cancelled, z0 into z0 becomes z0 square by zl. See here, zn is equal to z0 into jz0 by jzl, and zn is equal to z0 square by zl, which is equal to zs. So this is the case, input impedance is inversely proportional to the load impedance of the quarter wavelength line. So here, see, Zn is equal to input impedance of a quarter wavelength line case. This input impedance of a line is inversely proportional to the load impedance, right? So according to the definition, see here, it is a lossless uniform line of length lambda by 4 and its input impedance Zin is equal to the inversely proportional to the terminating impedance, means which is equal to 1 by ZL, and here in the numerator we'll get here as value Z0 square. Okay, so for a quarter wave length line, the input impedance is equal to the inversely proportional to the load impedance or terminating impedance, then that is the case Zn is given by Z0 square by ZL. Okay, so this is the second relation of lossless quarter wave length line type. So this is also called as impedance inverter. Okay, why? Because input impedance is inversely proportional to the load impedance, hence the name is given as impedance inverter or quarter wavelength line. Okay, then third type of wavelength lines is given by, depending upon its wavelength, the name has given eighth wavelength line. Hence, it is a lossless uniform line of length lambda by 8. Right? So, before going to discuss about this lossless uniform line, let me consider first law for the input impedance of a lossy line. That is, Zn is equal to Z0 into ZL plus Z0 tan H gamma L by Z0 plus ZL tan H gamma L. So here also, if gamma is exist, means propagation constant gamma constitute attenuation constant alpha and the phase constant as beta. If alpha is exist, then the name has given for this is lossy transmission line. To get lossless transmission line, we are supposed to assume alpha equal to 0. Then gamma becomes J beta. Now from this case, tan H gamma L is equal to tan H J beta L, which is equal to J tan beta L is the, according to the hyperbolic functions, trigonometric formula is given by tan H gamma L is equal to J tan beta L, right? So if you substitute in place of tan H gamma L by J tan beta L, it consisting of only imaginary part. Hence, the name has given here, it is a lossless uniform line of the length having lambda by 8. Hence the name 8th wavelength line. And its input impedance Zn is equal to the inversely proportional to the terminating impedance. Now, it is the magnitude of that is Zn is equal to modulus of terminating impedance. That we are going to derive now. Now for a half wavelength line, see, for a 8th wavelength line, L is equal to lambda by 8, and as we know that beta equal to 2 pi by lambda. According to the wavelength, then lambda is given by 2 pi by beta. Now from this, beta can be given as 2 pi by lambda. Right? Beta is the phase constant and lambda be the wavelength of the line. Right? For a 8th wavelength line, L is given by lambda by 8 and beta equal to 2 pi by lambda. Now, Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Means, in place of for a lossy transmission line, tan H gamma L is replaced by tan H J beta L according to the lossless. Then, if we substitute tan H J beta L by J tan beta L for a lossless uniform line input impedance, Zn is given by Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Right? So Zn is equal to, now Z0 into ZL plus JZ0 tan, if we substitute beta and L by 2 pi by lambda into L by lambda by 8. So lambda gets cancelled, 2 and 4 gets cancelled, pi by 4 is left out. Right? So if you simplify these two, lambda, 2 and this gets cancelled. Here also lambda and 2 and this gets cancelled. Then Zn is to be obtained as Zn is equal to Z0 into ZL plus JZ0 tan pi by 4 by Z0 plus JZL tan pi by 4. Okay, so this is the relation which we have simplified based upon beta value as 2 pi by lambda and L value to be lambda by 8. Right? So if you simplify those two, then we are going to get here Zn is equal to Z0 into ZL plus JZ0 tan pi by 4 by Z0 plus JZL tan pi by 4. Okay, so see, Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Now if you substitute beta by 2 pi by lambda and L by lambda by 8, then it becomes this 2, means 2 pi by lambda into lambda by 8 gets cancelled, then pi by 4 is to be left out. Now from this, Zn is equal to Z0 into ZL plus JZ0 tan pi by 4 by Z0 plus JZL tan pi by 4. Okay, so as we know that tan pi by 4 value is nothing but 1, that is given by sin pi by 4 by cos pi by 4, nothing but sin 45 by cos 45. As we know that sin 45 value is 1 by root 2 by cos 45 value is also 1 by root 2. Both gets cancelled, which is equal to 1. Hence, tan pi by 4 equal to 1 or tan 45 equal to 1. Right? So if you substitute here in this tan pi by 4 by 1, then it becomes Zn is equal to Z0 into, in the numerator we are left out with ZL plus JZ0 by, in the denominator, Z0 plus JZL. Right? So in order to simplify this one, again in order to get clear the relation between input impedance on the characteristic impedance Z0 or else load impedance ZL, we must consider, see, ZL plus JZ0 be there in the numerator, Z0 plus JZL is there in the denominator. See, if you observe in the numerator, ZL is the real part, Z0 be the imaginary term. And in the denominator, Z0 be the real term, ZL be the imaginary term. So to get cancel each other, we are supposed to consider magnitude of this particular thing. As we know that Z is a variable which is having real part as X and imaginary part as Y. So Z is equal to X plus JY is a complex one. If you find its magnitude, modulus of Z becomes root of real term square as X square plus imaginary term square as Y square. Right? So mod Z is equal to root of X square plus Y square. Like this, if you find this one, root of this thing, Zn is equal to Z0, means magnitude of Zn is equal to Z0 into, in the numerator part, root of real term square as ZL square and imaginary term as Z0 square. by in the denominator part also real term square as Z0 square and in the imaginary part as ZL square. So if you observe here, again in the numerator part we'll have root of Z0 square plus ZL square, and similarly in the denominator also root of Z0 square plus ZL square. Okay, so if you observe both are similar, hence both gets cancelled. Hence magnitude of this Zn is equal to what we have left out, Z0, that is characteristic impedance of a transmission, lossless transmission line, right? So modulus of Zn is equal to Z0. This is for lambda by 8th wavelength, means nothing but 8th wavelength lossless transmission line, right? So this is the case, means it is a lossless uniform line of having the length of this one is given by lambda by 8, and its input impedance, means magnitude of the input impedance of a lossless 8th wavelength line is equal to the characteristic impedance of a transmission line as Z0. Right? So in this lecture, what we have discussed is we have classified the classifications related to impedance matching as depending upon the wavelength and depending upon the stub matching. There are 3 cases in the wavelength lines. Depending upon the wavelength lines, one is said to be half wavelength, and second one is said to be quarter wavelength, and third one is given by 8th wavelength line. And depending upon the stub matchings, single stub matching and double stub matchings. So in this particular, we'll be concentrating on only this depending upon the wavelengths of the transmission lines. So for the first case, lambda by 2 case, input impedance of a lossless transmission line Zn is nothing but load impedance or terminating impedance. Okay, and second case, if you consider the wavelength of is as lambda by 4, this is the case Zn is given by inversely proportional to the load impedance or terminating impedance as Zn is equal to Z0 square by ZL, where quarter wavelength line transmission line is also said to be impedance inverter. Why? Because input impedance is inversely proportional to the load impedance as ZL. And in the third case we have been discussed, that is length of line is given by lambda by 8, and input impedance means magnitude of the input impedance of a lossless transmission line modulus of Zn is equal to, that is characteristic impedance of a line as Z0. Right? So in all the cases we have been evaluated the lengths. First we have considered as lambda by 2 for the half wavelength line, and the lambda by 4 is for quarter wavelength line, and lambda by 8 is for 8th wavelength line. Then in all the relations we have been evaluated the input impedance, how it is related to the load impedance or terminating impedance, or input impedance is related with the characteristic impedance, right? So in all the cases here, to evaluate this one, we are considering lossless transmission line and the lossy transmission line input impedance relations. So Zn is equal to Z0 into ZL plus JZ0 tan H gamma L. Sorry, there is no Z J here. Z0 tan H gamma L by Z0 plus ZL tan H gamma L is for lossy transmission line, right? Why lossy? Means if gamma is exist, gamma is nothing but alpha plus j beta. Now alpha is there means loss must be there, hence the name has given lossy transmission line, right? So if alpha equal to 0, then gamma becomes j beta. This is the case. Input impedance relation Zn is given by Z0 into ZL plus j tan beta L by Z0 plus JZL tan beta L. In all the cases, we are going to will be defining the length of the transmission line and phase constants. So in each and every case, L is equal to lambda by 2 as the first case, L equal to lambda by 4 is the next, and L is equal to lambda by 8 in each and every individual cases. For half wavelength line, quarter wavelength line, and 8th wavelength lines. Now, if you substitute L by all these 3 values and beta is common for everything, then beta is given by 2 pi by lambda. Depending upon these two values, L and beta, if you substitute 2 by these two relations in each and every cases, then we have been derived the three relations as for half wavelength line as input impedance is equal to the load impedance or terminating impedance, and for quarter wave impedance, quarter wave length line case, input impedance is inversely proportional to the terminating impedance or load impedance, as well as in the third case, magnitude of the input impedance is equal to the characteristic impedance of a lossless transmission line. Next lecture, we are going to discuss about the second case of impedance matching. Is important one is related to stub matching. There are two cases of stub matching techniques are there: single stub matching technique and double stub matching technique. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.